And then let me get the assignment up here. We'll kick off what we're doing today. Here we go. All right. Today, we are going to cover reactive programming again, but we're going to get down into some of the nitty-gritty on reactive programming. We're going to go over a couple libraries. We're going to go over what the interface looks like for a pub sub hub in Java. And we're going to do something we're going to wrap our heads around a use of a pub sub in Java, right? And for those of you that have already done publish and subscribe before, by show of hands, how many have already done publish and subscribe architectures before? Just use your little hand. All right, Jonathan has. Okay. We'll talk about publish and subscribe and the benefits of it. And then we're going to kind of throw it on its ear a little bit. And we'll look at some abstractions of, that sit beneath the pub sub design pattern. And we're going to do that with React and reactive programming. And then we're going to go over 5 different programming paradigms and compare them. These are the sorts of things that will show up on tests. Just a heads up, okay? Okay, let's kick things off. Reactive programming paradigm. Remember, there are 4 aspects or 4 principles in reactive programming: responsiveness, elasticity, resilience, and message passing. Those are the 4 biggies. Those will be important. It will be important for you guys to be able to describe what those are and give examples in those for the test coming up, okay? When we talk about reactive programming, remember, we're talking about the ability to compose asynchronous operators that are event-driven, so that I can take stuff that are coming from a publisher that's publishing events. I can transform that before it gets out to a set of subscribers. So that's the whole concept behind reactive programming, which fits into the reactive programming paradigm. Okay. This is review from last week. Any questions on this? We understand this concept, right? Okay, let's take a look. Specifically, let's look at the Reactive Java Streams API. Now, what's important about this is we're going to use Flow, Java Flow, right? And what's important about this is it provides interfaces, not implementations in this thing. We're going to talk about the different implementations of these interfaces. There's some basic ones, but we're going to talk about the newest one that we're going to use in ours, which is Reactor. Okay, so we'll talk about that. If I look real closely at Flow itself, Flow contains 4 different interfaces. The first one being subscriber. Now, what is a subscriber? Who can explain what a subscriber is? Anyone? How many of you have subscriptions to Netflix? How many use your parents' subscription to Netflix? No? Oh, Elle has her own. That's good.
They use mine. Yeah.
They use yours. There you go. So if you're a subscriber, that means that you have said, I'm going to use this service and I want to be notified when something changes or when I get an event. That's the idea behind subscriber. I'm going to subscribe to specific events that are going to happen. And most of the time you have a pub sub hub bus where messages get sent on the bus, and then a subscriber is just going to say, tell me all of the messages that I'm looking for that I subscribe for, notify me when they come. This is a very common asynchronous programming paradigm. It's used very extensively in very large systems. Some of the most prevalent publish and subscribe projects or tools that are out there, you guys know the names of. You've heard them before. A famous one that came out of LinkedIn. Anyone know the name that came out of LinkedIn? Starts
Is
with
it
a K.
Kafka?
Kafka. Thank you, Jenna. It's Kafka, right? Kafka came out of LinkedIn, right? Probably the most used pub sub hub out there. There's other ones out there. Who can throw out some other publish and subscribe message buses?
WebSphere MQ.
Yeah, MQ. Very good. Message queue. That's a good one. Another one?
I think Apache Cupid, is that one?
Yep, it sure is. There's a whole bunch in the Apache framework. Apache Pulsar, Cupid, Redis, believe it or not, is being used as a message pub sub hub now.
How's that work?
It works really well, actually.
Oh, interesting. I know RabbitMQ was a thing for a while.
Yeah, RabbitMQ is another one. There's a whole bunch of these out there, and they all have different characteristics and different benefits. When we look at the Java concept, what they've done is they've created these interfaces that kind of embody all the different types of publish and subscribe out there. So we're going to look at how these interact with each other and what the interface is. Then we're going to look at specifically different implementations of this. Okay, so subscriber, inside there, it's defining messages on and hook techniques on how to implement a subscriber, and then how I'm going to interact with a publisher. So things on here you're going to see are like on subscribe. When, I've subscribed to something, I got notified that the subscription is ready. I've got error handling. I've got on complete and on next. Now, this is really interesting because most of the time in a publish and subscribe, the subscriber just says, I'm listening to events. In reactive programming, you can actually say, I want a certain number of events. And then it's going to give you back that number of events, or a certain number of events I'm looking for. Okay. And we'll talk about the interface on that. Okay. So that's the subscriber. We all understand subscriber. They're receiving events. If a subscriber is receiving events, then what is a publisher doing? Anyone?
Producing the events.
Producing the events, right? They're publishing the events out onto a bus, if a bus is being used. So that's pretty simple. They're going to publish things out on the bus. For the interaction between the publisher and subscriber, I'm going to get a subscribe message for the publisher, and then I'm going to create a subscription that then becomes the interaction between the subscriber and the publisher. So this decouples the publisher and subscriber from each other, and this is how the interaction is going to go through the subscription. Okay. Now this is specific for a reactive API that we're talking about. Okay. The publisher, and I'll show the interaction in the flow. Then I have a processor in here that is attached as well. And the processor is the thing that is going to be able to interact between the subscriber and the publisher. And those processors there, that's where I can jam in those operators that I talked about. So I can do my transformations between the publisher and the subscriber through the processors. Okay. All right. Let's take a look at flow specifically and the interface with flow. So a subscriber here is going to actually tell the publisher, I want so many items from the subscriber that I'm willing to accept. Now, this is very different than traditional publish and subscribe, where the publisher and the subscriber don't even communicate with each other directly. They communicate through the bus, and the subscriber just starts grabbing onto a feed. Like in Kafka, they're called topics. And the topic is pretty common throughout all of them. Sometimes they use the concept of queues, where a subscriber will subscribe to a queue and publishers will publish on a queue. In this case, with Flow, a subscriber can actually inform the publisher how many events it's willing to take. Okay. And then it's the job of the publisher to send the acceptable number of items out to the subscriber. Both of these here combine two patterns. One is the pool model pattern, where I'm saying I'm going to pull information from you. And the other one is the observer pattern, which I'm going to push information out to the subscriber. So Flow kind of combines the two together into something that I'm more used to using in traditional programming, where I'm calling a method and I expect a return. But this happens asynchronously, and that's critical to understand. Okay. Altogether, these things, this will allow the subscriber to say, I want this number of events, and I'm going to get that number of events back from the publisher. Pretty straightforward. Okay. Let's take a look at the interaction between the three main interfaces here: the publisher, the subscription, and the subscriber. So first, the publisher will say, hey, I'm going to publish something. Anyone want to subscribe to me, right? So on subscribe hits, the subscriber says, yes, I subscribe to you. I'm ready to go. So now the subscriber says, okay, I now have someone that I can ask questions of, right? I can say, I want these events. It's going to send out a request for a number of events. And that is a one-way communication. It's asynchronous, non-blocking. So I'm going to say request in number of events, right? This is critical that it's non-blocking, right? I can call cancel anytime I want to cancel those requests, because let's say that I send out that request for 10 items and I get the first 5 right away, but the next 5 could take 5 or 6 hours. Well, I don't want to wait around 5 or 6 hours. So I could put a little time loop in there and say, cancel the request that I have before. Right? I don't need any more. 5 is good enough. And if you can only give me 5 in 5 minutes, that's good enough. I want 10, but you only gave me 5. So that cancel gives me that ability to cancel the request that I made. Anytime that, and I'm making that to the subscription, not to the publisher directly. This subscription becomes the intermediary or the proxy for on both sides, for the publisher and also for the subscriber. So any requests that I send in to the subscription will be forwarded on to the publisher. Hey, someone requested this number of events. So it will then return it. The way it returns it is it returns it as individual async calls back, like on next is the method that it uses. And I pass in to on next data that the subscriber is going to get that information from. Then when I'm all done with all 10, I'm going to call I'm done, complete. Now, you would think that the subscriber would just count the number that it got. Why does it need an on complete? Any ideas?
Because they're asynchronous tasks and they probably need time to complete. They need to send some sort of message.
Yeah, remember, this is all message driven. There's no guarantee when I send a one-way message that it actually arrived.
Yeah.
So that just signifies that the publisher's finished sending all the data?
Yep, that's exactly right. That's exactly right. I am done sending the data. So what if the subscriber itself only received 8? It asked for 10, and then it received 8, and it got an on complete. What happened to the other 2?
They must have failed in some way.
Yeah, they could have failed, or maybe things got out of order in the way that they came through, because you're dealing with a network. You're dealing with a lot of things in the middle. You're not guaranteed, right? So this is one of the downsides, right, to these kind of architectures. And any microservice architecture you have, when you're communicating between microservices, you're not guaranteed the other side is actually going to receive it unless you do a return response. right? Which can double the amount of traffic that you have between microservices. These are all one-way calls. So if I run into that situation where I did not get all the information I got and I got non-complete, I now have a situation that I need to deal with in code, right? I need to say, I didn't get everything I needed, or you can say, that's good enough, whatever you want. But this gives you the ability to at least determine that you got everything that you wanted. There's also an on air. So if something happened on the publisher, I asked for 10 things, it can only find 5, and then something happened, corruption in the data or whatever, I can throw an on air and I can actually throw in an exception. So this gives me the ability to do distributed exceptions from the publisher to the subscriber. So this is another way of handling and making your architecture resilient, because now your subscriber can get exceptions that have been happening on the publisher, if that's what you need. Okay. All right. Any questions on this? This is understandable? You get it?
Yeah, is this an example of a poll style pub sub architecture, or which?
This is using a pub sub architecture specifically for flows, right? And reactive programming. Remember, reactive programming says I'm going to inject in between the publisher and the message that comes in the publisher. I can inject operators in there to change the information before I spit it out to the subscriber, right? This pattern here that we see here is a pattern that's used specifically in the Java Flow architecture, right? There's several different implementations of this, and we're going to go over 2, and we're going to stick on the Reactor one primarily. Good questions. Okay, so remember, popular implementations, we'll talk about them. I got something publishing data, like a Twitter feed, a publisher. I'm going to do my event transformations in here. My operators are going to merge, filter, map, right? And then they're going to publish that out onto the subscribers. The subscribers are going to get a Twitter feed that has maybe sentiment analysis. I can see how all my users are doing. Or if we did it in class, I could see that everyone's bored out of their mind from their Twitter feeds that I've been collecting while you guys are sitting here in class, right? So that's the concept behind it. Publishers, my event transform, which are my operators, and then my subscribers are getting something on the other end, right? That's valuable to them, and that's how I go. All right. Okay. So we've covered this before. The key, this is really important to understand how this works, is that the reactive streams are actually implementing the concept between the concept of the operators between the publisher and the subscriber. So in these reactive streams, just like in other streams that I had, I could put filters and I can do all that work. I can do the same thing in reactive streams, but I'm doing it between a publisher and a subscriber. So they could be in different processes, different microservices. They could be all over the place, right? That's the benefit. This allows me to scale, which is one of those key attributes of reactive programming. Elasticity, message passing is another one. We're doing this via message passing. Okay. All right. Questions on this? We understand how this works? All right. Let's talk about 2 specific reactive programming libraries. How many of you have used any of these 2? RxJava? Anyone use RxJava? Raise your little hands, your virtual hands. No? Good, because it's complex. It's part of the Reactive X family, which has multiple language mappings. It was credited by Netflix. It's pretty mature out there, but the learning curve is pretty high. It's because it supports multiple languages, you have to understand the abstract concepts really well. And I think it's probably a little bit over complex. for what we want to do. And it includes in it a lot of things that Spring already provides for us. So we're not going to use it, right? It's more than what we want to do. We're going to use Reactor. And Reactor was based off of Spring. So they could simplify a lot of things and reuse the concepts that are in Spring already. It was created by a company called Pivotal. Do you guys know who Pivotal is? Anyone? Pivotal was a really cool in Silicon Valley, right downtown San Francisco. They were software engineers for hire. You could hire whole teams of software engineers to go do something. They ran it completely agile, very cool, very fast moving type of company. They got bought up by VMware. They ended up being a consulting arm for them. And then they got folded in over the years into consulting services. But out of Pivotal came a lot of really good things, including the Reactor library, right? It was built with Spring in mind, and it's specifically WebFlux, which we're going to take a look at. And it's very simple and highly performant. So it's going to take advantage of some of the things we've already learned about on Spring, including threading and threading models as well. Okay. Oops, I went too far. So if I look at the AI design here between the two, this may show up on the test, just so you know. RX Java is multilingual, or the RX family is multilingual, right? They have the same interfaces, but different implementations based off of different languages. It's a very rich API. It has a lot of operators involved in the, because we're all about writing those operators, including map, flat map, filter, zip, merge, among a whole bunch of others that are out there. But it is pretty complex. Terminologies, they have the concept of, they use an observer pattern. So you're going to see a lot of terminology that are in the data observer view pattern, which is observable, single, things like that. Observable means it can emit multiple items, and single means it emits one item coming out of it. And then maybe, which I think is a funny name, emits one or none. It might come out. And then it's an interesting interface, but very verbose, which you would think would fit really well with Java, because Java is known for its verbosity, right? Sure, you guys already know that. The Project Reactor, very minimalistic. It has two concepts, mono and flux, and a third one that's kind of that they call parallel flux, but it's flux that can run on multiple threads. But the concept here is that mono represents a single value or no value can come out of a mono, and a flux is a set of operators that can produce multiple values, 0 to n. So 0 to n values, and it maps really well with Reactive Stream specification already there. So it's a lot easier to use, specifically geared towards Spring and leveraging on top of Spring. So it's lighter weight. It's targeted directly for Java Spring. Okay. If you're out there looking to do reactive programming and you're looking for multilingual, which one would you choose?
RX Java.
Yeah, RX. You'd choose the RX framework because you've got Java, Node.js, Go, Rust. There's a whole bunch of them out there. Okay. All right. There's a concept that you guys need to understand as well. And the concept is called back pressure. So anyone have an idea what back pressure is? Anyone can describe back pressure? Anyone ever flood a toilet?
Yes, I have done that.
Okay, thank
but
you, Aaron.
back pressure, yeah, when you can't process fast enough and you have to basically say, hey, slow down, I can't handle all this.
Yeah. So where's the back pressure coming from, Aaron?
Usually it's, if you're a microservice processing messages, you're taking some action, which is probably calling downstream systems or something, and your threads are all filled up, or you're starting to run out of resource because you're waiting usually.
Yeah. So you're getting all these events and you just can't handle them fast enough. So they're piling up. There's back pressure, right? So in this paradigm, in the flow paradigm, back pressure is coming from the subscriber. It means the producers, the publishers, are publishing faster than the subscribers can handle it. Just like Aaron said, right? Because that subscriber, maybe it's has a lot of processing it's doing itself, and it just can't handle all the events that are coming in. You can also have this problem where there's multiple publishers and one subscriber. And so they're being overwhelmed. So with back pressure handling, it means that the framework's going to handle the back pressuring for you, right? Or you have to program that in yourself, which means I'm going to accept the events and maybe queue them up, store them in memory, or store them on disk, which is slow. But there's different mechanisms. In RX Java, they give you a lot of fine detail on how to handle back pressure. On Reactor, they handle it for you. It's designed in right up front. So you don't have a lot of configurability, and they go for convention over configurability, which means it's easier to use, but you're stuck with the model that they came up with. That makes sense? These types of trade-offs that you see when selecting a library are very important to understand. Configurability tends to mean more complex to set up. Like those people that love VI as an editor, you know what I'm talking about. But once you learn it, you can do crazy things with it, right? But if you don't need all that crazy things, then configurability really doesn't pay a lot of benefit, and convention is more likely a better way to go. So if I look at RX Java compared to Project Reactor with back pressure handling specifically, configurability for RX Java, convention for Project Reactor, right? It handles it for me. I don't worry about it. I don't care about configuring it. It just takes care of it. Okay, does that make sense? That when you guys are working with new libraries or new technologies, look for that. Do I want high configurability? Yes, great. It comes with a little more complexity. Or do I want convention? Yes, it comes with handcuffs. It comes with guardrails, right? It restricts me. Okay, we are going to use Project Reactor. So let's dig into it and find out exactly what it does, because you guys are going to be using this. All right. I think we already started using it in 2B. I'll have to go back and double check. So mono means what? One, right? For us, it means 0 or 1 coming out of a mono, right? So I'm going to either produce something or I'm not, right? It's asynchronous. So it's an asynchronous computation, which is important to remember. They use a cold stream model, meaning it only starts work when it's subscribed to. So if I'm subscribing to this mono, it will only be starting its work when that happens. Okay. That's important because in the traditional publish and subscribe, there is no connectivity between the subscriber and the publisher could just be publishing stuff for a long time with no one subscribing to it. In this model, because of the reactive programming, we're saying that a mono will not fire and start working until someone subscribed to it. Okay. Completion is different in mono than in flux. Why do you think that is? very simple. Remember, we have the on data and on complete hooks. For a mono, when I call on data, it's implied on complete as well. If I call an on complete with no data, that means, you know, an on complete comes from a mono, that means there was no data. If I get an on data, it means I got the data and I'm done because it only came through once. You got that?
That makes sense.
Okay. All right.
Yeah.
Remember, the use case for this is I just need one data. I just need one piece of data out of it. That's it. One or none. So this could be used as a conditional statement. It could be used as a lot of things, as a switch. It could be used as a lot of different things. A mono. Okay. On the flux, flux represents 0 or more items coming through, right? It can emit 0 items or tons of items, right? Asynchronous, just like before. Let's see what else. Cold stream model again. It only starts the flux once it's subscribed to. This can save resources, but it also means there can be a delay. You might think that, hey, that flux is off there doing work for me. It's not going to do anything for you until you subscribe to it. Okay. The big difference between mono and flux is an on complete must be sent. Right? In the mono, I can just do an on data. On a flux, and on complete must be sent when I'm done. Right? And then air handling is handled with the on air, just like in mono as well. Use cases for this could be sending sequences of values over time, like streaming data, reading a file line by line, or event handling, where I'm going to send a whole bunch of events through, right? It's also very useful for sending items that I can emit a number of values, but not all at the same time. So like an API that returns multiple results, right? And maybe it's too big to send in one big blob. I can send it this way. So those are the differences between mono and flux. All right. Pretty simple when you, if this were on an exam to describe it, I would say it'd be very simple to say mono handles 0 to 1 items and flux handles 0 to more items. And the real big difference is in the completion. Understanding the completion in a flux and a mono are slightly different, and describe that. That might show up on a test. Okay, let's take a look at what this might look like, right? So mono, I create a mono here. Mono uses a template. So I'm creating a string mono, and it's just going to say hello reactor, and someone's going to subscribe to greeting, and it's going to print it out, and pretty simple. And you'll see where we can use this in lots of different places. Common operations on here on a mono, because I can have the operators, are map, flat map, which can flatten out a map, right? If I have nested maps, I've got an on-air return, a do on success. If I get something successful happen, I can then do something. And then I can also block if I need to, right? I discouraged blocks, but they're great for debugging. In production, though, you could block a thread, which you don't want to do. Okay. On the flux side, this is what flux could look like. A simple example where I've got a flux of integers that are coming in, and I'm going to get all 5 of those integers coming through. Right? Again, same concepts. I've got map, filter, flat map, and I also have merge and concatenate. These are different than on mono, right? I can't call merge and concatenate on mono, but I can on a flux. Okay. Any questions on those two? Nothing? All right. That's a high level of the reactive engine. If you want to learn more, I suggest ask your friendly chat GPT, Gemini, or Cloud and they can help you a lot with understanding. If you don't understand a concept, have a great conversation with them. They can help explain it in detail. Okay. They are old enough where they are trained in those models already. Okay, back to reactive streams and principal mappings. We're now going to map what we saw with Reactor. We're going to map those and see if it covers all of the reactive principles that we have. Remember, responsive, elasticity, resilience, and message driven. Okay, so the first one, responsiveness. To make sure that you are still following it, avoid blocking caller code. So that block that you had put in there for mono, make sure you take that out. Otherwise, you've kind of broken the whole concept, right? Take that out when you're done debugging, right? Also realize that if you are using these things, asynchronous programming means you have to program defensively because you do not know the order that you're going to get things. Okay, so that's important to understand. Another thing that they suggest for responsiveness is don't change threads as you're moving through. By default, operators will stay on the same thread as the previous operator in the chain, unless you need to spin out a new thread. I would prevent doing that if you absolutely can, because it will increase the overhead and synchronization of those threads, right? And most of the overhead is happening down in the OS layer with context switching and memory caching and things like that. So you could go hog wild crazy with your threads and say every instance of every operator is its own thread, and you'll actually slow things down on an individual machine. Okay, so pay attention. There are some fine-grained control over mapping events to threads, and so pay attention to those things and make sure that you're not going hog wild crazy with threads. Otherwise, you'll lose your responsiveness. What's this one? This one is resiliency, right? Take advantage of the on-air throwable when you're programming. If I do have an error in an operator, go ahead and throw that error so that it can be caught, and that will make your subscriber more resilient. I got that error. I know what to do with that error. Like maybe I am calculating prime numbers or doing some factorization, and I run into a not a number error. I want to throw that out and say, hey, I found something in here that was not a number, so we've got an issue. So resiliency, it does provide for on air, so it does a good job with the mapping, but you have to use it. Okay. Elasticity. So as you need to use threads, use them, but don't overuse them. So you have to know that there's a trade-off. But this does give me the ability to spin up threads and bring down threads based off of the load that I have. I can do that kind of work, right? Oh, there's a beautiful typo. I can't type thread. I don't even know how to say that word. Turhead. That's close. Like I mentioned before, most of the operators will continue working on the thread previous on the same thread as the previous operator, unless you actually specify the difference. And the initial operator will run off of the thread of the subscriber itself. Okay. Not the subscriber, the same thread as where subscribe was handled, sorry, which is in the producer or publisher. Okay. All right. So here's an example. If I want to start a new thread for a mono, this is just a simple example. So I've got my mono that I kicked off there. I've got my thread that I kick off with a new thread. That should be an equal sign, I think. Yep. And then I'm going to now do that subscribe. So in this case, the mono is on its own thread. And Very, very simple. And there is a typo there. So let me fix that typo. Okay. All right, any questions on that? Okay, last one here is message driven. So even though you guys aren't going to see it when you're programming, underneath the covers, Reactive Streams is using message passing internally between the thread pools that are there, right? You can, and which is really cool, because all you have to worry about if you're using a fork and join between the thread pools, you don't have to worry about a message passing. It's handled for you. So you don't have to worry about any of that stuff. Okay. Like I said before, don't go too crazy on the threads, because it will slow things down. Okay, so now can you see how the reactive streams fits the reactive programming model? I would hope so. They use the same word, but it hit all four of those areas. Okay, before we move on to this next part, any questions? And I'm going to take a little stop. Any questions from anyone? I know it's a lot to cover. All clear as day. Remember, reactive programming is a different paradigm. We're going to cover 5 different paradigms right now. Actually, 4. One is a combination that kind of mimics reactive programming. Okay, no questions? You guys all understand? Oh, okay. All right. Let's keep going. Let me share again. All right. All right, let's talk about these 4 different programming paradigms. The one that you guys are probably most used to is traditional blocking operations, object-oriented programming. And with Java, it's built in, right? When you think about that, it's single value, synchronous blocking. It's you guys are used to this kind of programming, right? I have an object, I can call a method on that object. I wait for the response, it returns. I can do try-catch blocks. It's really easy to program in. That's what we're primarily used to. But the cons to this are it could be inefficient, and it may not be suitable for method calls that are really long in duration. And long in duration is a relative term. If I'm doing real-time programming, the long in duration, it can be in the milliseconds. If I'm doing a website, long in duration could be 2 or 3 seconds, right? If I'm doing weather prediction, long duration operations could be days, right? So it all depends on what you're working on. So it might be that object-oriented programming paradigm is the right way to go based off of the type of program that you're writing, right? But remember that it can be inefficient, and especially for those long duration operations. Okay. This kind of stuff is going to be on the test, guaranteed. Okay. Let's look at streams. You guys have already played around with streams a little bit. Oh, well, here's an example of object-oriented code, right? I create an array of output stream. I'm reading the bytes in. I'm writing the bytes out, or I'm just writing the bytes out, right? Someone passed me a URL, and I'm opening the stream and then writing the bytes out to another stream. Pretty straightforward type of stuff. Okay. Is this still under object? Oh, I have the concept of virtual threads. We've done this in class in the assignments, and structured concurrency for making synchronous programming cool again. This was actually very synchronous programming is something that we're used to doing, and watch for this, because we did use that in that first part, because synchronous programming is easy to understand. I call a method, I wait for the return, I get the return, I use that value to do something else. So it's very structured the way I do it. All right, let's take a look at streams. You guys have been using Java streams. We've been kind of forcing you to in the assignments. And it enables function style operations in streams. So you guys have seen this before where we would use filter and things like that, right? It's very elegant operators. It's easy to understand. I'm working with collections, and it's good for both CPU and IO bound tasks, because let's say I'm processing a gigabyte file as it's coming through. I don't want to read the whole thing into memory. I can just put a stream in there and stream it through the operators that I have, right? There are some problems with it. It's not inherently parallel unless we make it explicitly parallel, and it's still synchronous. So which means I'm still blocking. So as I'm reading the stream through, I'm reading data through the stream, I'm still blocked as I'm waiting for it to all come through. Okay. All right. Here's an example of a stream. So I got get input. I got a parallel stream here. I'm filtering it. I'm mapping it. I'm doing a multi-map, and then I'm converting it to a list. And so pretty straightforward, easy to understand concept, but it's still synchronous. I'm not going to return until it's done with all the steps there. Okay, let's take a look at completable futures. You guys remember futures from the assignments, right? This is the concept of promises in the Node.js realm, and many of the other programming languages. You have the concept of promises built in. Now, with Java, they've added it. And it means that I can now start playing with asynchronous programming with single values, where I can say things like, give me a list, but it's an asynchronous call. So it doesn't return the actual list. It returns a future to a list, or you can think of it as a future pointer to a list. And then it can, it's non-blocking. So then it can continue on with other things until that future is resolved, or that promise is resolved or kept, and then it can move on. So the pros on this are it's non-blocking, which means I can improve performance of my application for IO bound tasks, because while it's waiting on that IO, it can be processing something else in the thread. It can be really difficult, and I have done this myself in Node.js with async, await and async completable futures. And it can be really hard to debug, because you're walking through the code, and if you don't do things right, the code jumps somewhere else and you don't know where it ended up, and you're just pulling your hair out. It's also can be very difficult to handle errors in this, because the control flow does not necessarily follow the exact way you have your code laid out. So there's some downsides to using it, but error handling is one of those, and control flow can be difficult to follow. It also, in that control flow, you're also not guaranteed the same order of execution every time you run a program, because you're non-blocking, you're waiting for something to finish, while you're waiting, other things can be happening. Okay. All right, here's an example of a completable future. We've shown, you guys have used these, but maybe not known that you were using these. So there's some things that we can dig into more on that if we need to. Okay, now in the reactive and multi-values and asynchronous, we've got two paradigms here. The first one we'll talk about is streams with completable futures. That's something that you can use, but we're actually going to use flows, which we'll show here in a second. But the benefit of this is I can improve performance when I'm dealing with multiple values coming through. I can improve my resource utilization and within a certain structured flow of control. And I can the benefits here is that I can now handle the multiple values asynchronously, right, without blocking and things like that. Complexity goes up quite a bit here, and debugging can be really, really difficult in this. If I'm jamming in futures into the stream and I have to convert from futures to data structure, it can be difficult to debug if you're having a hard time, right? Here's some examples of what that might look like. It looks like a normal stream, but there's asynchronous futures in there that are running through there. Okay. All right, reactive streams. So this takes that next level up. It's very similar. The benefits are very similar to what I got with streams with completable futures, but it handles a lot of the complexity for me, like non-blocking back pressure, composability, and then concurrency. It leverages the concurrency model, makes it easier for me to program in. The downside is that there is a steeper learning curve because I have to learn a new library. I'm learning a new way of doing things than, taking a stream and just using futures in it. And it can be more complex at first to understand and to use appropriately. But once you do, it's actually easier to debug than the streams with completable futures. This is what this kind of looks like. Just a simple example. I created a flux here. Remember, flux means there's 0 or 1, 0 or more, sorry, items. And then from here, you can see that I've got several different things that I can do with the flux as it's going through the operators there. If you look, do you see any message passing here that's going on? None, but it's happening underneath the covers, as we talked about before. Okay. That is it on the lecture stuff for today. There was a question in the chat. What was the question in the chat? I just saw it.
Yeah, I was just asking, like, the project reactor, that's the one that does support back pressure, and
It does support back. It handles back pressure for you. There is a little bit of configuration, but not much.
Okay, so it's just very limited for the manual stuff. Okay.
Yep. And we will be using Project Reactor in 2.2b, I think, 2b or 2c. Okay. All right, let me hit